Get that. All right. All right. Well, so I also want to thank the organizers. This, as Helen had mentioned, this workshop actually kind of came out of some of the, many of you may be familiar with the pre-AGU events that the GeoPRISMS office used to run, with the idea of it was convenient because people were already around, and so you could gather people pretty much on the cheap for sort of a quick mini workshop. And in 2019, we were thinking about the sunset of the GeoPRISMS program as a formal program at NSF and as a community program, and sort of at the same time a community of 600 plus scientists who were really energized doing amazing work. And we didn't want to, as I said yesterday, just celebrate the party's over, go home. And so how do you do this? These workshops are outcome of thinking about strategies to keep the community engaged and begin thinking about what could be next, whether it's a more of a distributed set of initiatives or something that NSF hears about from the community saying, there's a real thrust in this area. So what I was asked to do today is to do a little bit of a kind of retrospective, I guess, and try to share what, from my vantage point, what we've learned through the GeoPRISMS program about plate boundary deformation structure and mechanics, or plate boundary deformation processes. A lot of what I'm going to talk about is not meant to be totally comprehensive, so I may leave out a few things here and there, and if that's the case, I'll apologize in advance. Most of this is coming from those research nuggets that PIs, so if you were a student through GeoPRISMS, and maybe that your advisor had a grant, maybe that your advisor asked you to contribute to that nugget. These are the sort of one-page extended abstracts that got submitted to the office, so we could kind of keep track of all the cool stuff that was happening. And then also we would do at our bi-yearly GeoPRISMS steering committee meeting, we would have report outs on all of the active grants in the GeoPRISMS program with summaries from the steering committee members sharing with the rest of the committee kind of what's the progress on the science plan. And so a lot of the content here has come from that kind of information gathering and synthesis. And then this photo in the front, for those of you, most people were here yesterday again, because there's so many early career scientists here, just amazing. You've seen the picture already. So it's a quiz. What's the picture of? Is anybody? Yeah. So this is a photo of the East African Rift system, and this is work that James Muirhead and others did looking at CO2 fluxes in that system and how that's related to the volcano. And even though I'm a subduction zone guy for the most part, this is still one. So I'm not going to belabor this because I think many people know it already. But again, just to kind of quickly summarize, so the GeoPRISMS program, one of the really, to me, a hallmark of the program was that it was community driven. Starting from the science plan all the way through all the workshops, and then even the kind of synthesis and sort of forward-looking part of what we're doing today is about people in the community, the scientists who are going to be doing the work, defining those questions rather than something that's been sort of top down. And then the other part of it, of course, is that it was very broad and addressed question. I say it was, but I know there's a lot of science that's still ongoing. Addressing first order questions about continental marbles. And so the primary parts of that, and I'll talk about that in just a second, are rift systems and subduction systems, two big initiatives within GeoPRISMS. And then the last bullet here is also a key point, and one that I mentioned yesterday, just sort of a reminder. And I think an important point thinking about going forward is that a big part of the impact of GeoPRISMS, the footprint of GeoPRISMS, was not and is not just the science that was funded by Jen's program at NSF. A huge amount of science was leveraged. The ideas came out of GeoPRISMS workshops or from GeoPRISMS PIs or from the GeoPRISMS science plan, and then it was implemented by international partners, by the drilling program, by other parts of NSF. And so there's a really outsized impact on the science that was done from what is otherwise a relatively small program in terms of sort of actual dollars at NSF compared to a lot of other programs. Okay, and again, this is something I talked about yesterday. I'm not going to belabor this too much either, but so there are two broadly integrated initiatives as part of GeoPRISMS, rift systems, and subduction zones. And in addition to those two geological or tectonic settings, there are also these cross-cutting thematic questions or topical, again, sort of cross-cutting themes that hit both. I just want to make sure that I'm not supposed to do anything about that.
No.
Okay.
That's me. Just like let me do this.
So of those, the last one is really obviously most central to this group, but one could argue that plate boundary deformation and geodynamics actually are interlinked with and affect many of the other things on that list. So, so what's exciting about this really is that plate boundary deformation is important for all kinds of plate boundaries. And I'll talk more about that in a second. All right. So again, rifts and subduction zones, and then within those, there are a series of questions. So these are kind of the specific questions that are from the science plan. So this was what we set out to achieve at GeoPRISMS in a really broad sense. And one of the things that I noticed is the 3 prompt questions that Helen showed, sort of that form the motivation for this workshop, all had the word rheology in it. Right? And so to me, that's a way of thinking about the problem, and that's kind of how I've couched a lot of the sort of discoveries and accomplishments of GeoPRISMS is whether that's rheology as linked to what we're imaging, or rheology as linked to what we're seeing in the geologic record. It's how do plate boundaries behave and what do we learn about them. And so these are just, again, I'm not going to read these out, but this is in the GeoPRISMS science plan. It kind of lays out some of those fundamental questions that are related to how these 2 kinds of systems behave and why they behave the way they do. And again, maybe this is just my own bias. Well, it's definitely my own bias. But for all of the questions that GeoPRISMS set out to ask, to address, plate boundary deformation processes are really central, right? So questions like, what is the rheology? What's the right rheology? What are the constitutive models that should be used in thinking about faults and wall rock and plate boundaries? What are the geological processes that take place at plate boundaries? What are the deformation mechanisms, and how can we learn from the geologic record how these systems are behaving in terms of their kinematics, their dynamics, and mechanisms? What are the interactions between rheology, fluids, and metamorphisms? What's the role of plate boundary strength in rheology and feedbacks with the deep earth, the driving forces, and the construction of topography? And then the last one, which you may not be able to read there, is cut off by the Zoom controls, is the importance of inherited structure on both rifting and subduction. So how does a plate boundary initiate, and what's the role of what was there before? Okay, so I was on a dare/$1 offer. It suggested that I used a whiteboard, and I learned that I couldn't. But so before I tell you what I think the fundamental advances are of the last 10 years of GeoPRISMS, I'm kind of curious what this group thinks of when they think of the accomplishments. You know, I'm sure everyone here has been reading papers and thinking about this in terms of your own work. So I want to see if I got it right. So what are some things that this group thinks are accomplishments of the program? What have we learned about plate boundary deformation? It's not like a quiz. It's actually a quiz thinking. I want to see, like, my next slide is what I think, and I want to know.
That we can get information from fossil subduction zones about active plate boundaries.
So I don't know if everybody heard that, but yeah, so sort of interrogating fossil plate boundary systems in the geologic record to learn about active systems. And that's both through margins, the predecessor program, and GeoPRISMS has been maybe not like the primary thrust in terms of where all the money went, but it's been absolutely, I think that's, yeah.
We have some new constraints on how the surface moves and performs GNSS observations.
So geodetic observations and new constraints on how deformation occurs.
Going offshore brings surprises.
Going offshore brings surprises. I like that. Yeah.
And it's complicated.
It's complicated. The more you see, the less you know. I think that's a lyric from a song. Huh?
Yeah, so we have better understanding of the variations in space and time of how like subduction zones are slipping. So how the megathrust slips.
So it's new information and new constraints on the spatio-temporal distribution of slip in subduction zones, and probably also in rift systems.
Connections between the solid earth and atmosphere and oceans, like your example of CO2 emissions from rifts, but also in turn the way that surface processes can modulate solid earth processes. It wasn't like one of our explicit questions, if I remember, but I feel like it's something that's come out of a number of different GeoPRISMS studies.
So again, for the folks on Zoom, in case you couldn't hear that, Donna, that was the feedbacks kind of in both directions between the deep earth, the atmosphere, and the lithosphere, basically. So impacting one another. Cool. Well, I don't want to cut off the conversation, but I also don't want to take a lot of more than my allotted time here. So maybe I can stop the talk now because I think you guys already know most of what I was going to say. I mean, a lot of the same, maybe said in different words here, right? But so what are some of the fundamental insights and advances that have been made, not just through GeoPRISMS, but these are places where GeoPRISMS related work, GeoPRISMS conceived work has really, I think, led the field or led to some new knowledge. And this includes the complexity of fault slip behavior. So this is kind of what Kaylee and Jeff were talking about, maybe getting at it from slightly different angles, but the what, where, and why of strain accumulation and release, the role of fluids in plate boundary deformation, and particularly linking improved imaging with physical properties and thermal metamorphic models, making inroads in connecting structural metamorphic and rheological observations. So this is, to some extent, I think the first point about taking the geological record and saying, what can we learn about what the deformation processes are in situ at depth in the real plate boundary or the active plate boundary. This didn't come up in the anything from the group, but there's been a bunch of work through GeoPRISMS in trying to better constrain the thermal state. So heat flow surveys and thermal studies, thermal models of subduction margins in particular, linking that to plate boundary deformation all the way down to the subarc, from the trench to the subarc and subduction zones, and from the top to the base of the lithosphere in rift systems. So that, of course, the thermal state affects the rheologies profoundly. And then the last two are maybe a little bit more like softer things, but super important. One of them already came up from Helen when she had people stand up and raise hands, right? Is that the workforce training is really astounding in terms of the number of people who did their graduate work or a postdoc as part of GeoPRISMS and then became leading investigators and PIs. And then the other part of it is this leveraging of other major programs, including IODP, other programs in NSF, NASA, and international partners. So what I'm going to do now is take you on a little bit of a tour that's maybe just a series of maybe, I don't know, vignettes, thinking about how GeoPRISMS has contributed with a couple of examples. Just because I'm sure people want to see some actual science instead of me just giving you lists of things. So going from top left to bottom right is sort of the evolution from the top left was actually a figure from Roy Hyndman's paper in the SEAS volume, which came out in 2007, sort of midstream in the margins program. And that was our view of the seismogenic zone of subduction process. There's an upper portion that creeps, a central portion that's seismogenic, and a deeper portion that creeps, either because the slab has intersected the moho of the upper plate or because it's hot enough that you cross the brittle ductile transition. And that was it. So there's a seismogenic zone. And then, of course, in the years, actually, even before that paper was published, there was a known observation of the spectrum of slip behaviors that included slow slip and tremor and low frequency earthquakes that not only fringed that seismogenic zone, but also occurred within it sometimes. And that led to a much more evolved model, sort of on the bottom right, is a variant of stuff from Subilic and Thornley, showing a more heterogeneous and complicated, but probably still not complicated enough cartoon of the subduction. And so there's, first and foremost, one of the contributions from GeoPRISMS related work was being able to develop this much more complicated model and ask much more informed questions about what controls earthquakes and slip behavior in real materials and with real faults. If you don't like Roy Hyndman's, you could use Chris Schultz's, but it's the same kind of simplified concept. And so in the GeoPRISMS science plan, there was a recognition, at least sort of a few years later, that there is this spectrum of slip behavior. But even this figure, which was sort of a collaboration between a bunch of us who were working on that, Kellen Wang and Chris Marone and myself and Julie Morgan, and put together this figure. It's a nice way of framing this question and sort of realizing that there are these different kinds of behaviors, but it's still not complicated. Right? So since the time that this figure was made 10 years ago, we already know that it's not as systematic or simple spatially, and we still don't really know, or at least at the time that GeoPRISMS started, we didn't know really what caused these things. We just knew that they happened. And we were actually wrong about where they happened. We really simplified this. So that's sort of point number one. The seismogenic zone, frictional transitions, and fault rheology are not nearly as simple as we had thought before. There is this spectrum of slip behavior, and there was a realization that we can try to dig in to understand not just the what and where, and not just the when, but also the why. What is the underlying control on how faults behave, how plate boundaries behave, and why they behave the way they do. Another sort of part of this story, and this gets to the point I think Zach you made, that when you go offshore, you find surprises, right? And so this was a significant kind of frontier area that's now becoming a little bit more, I don't know, sort of the norm, is offshore geodesy. And so this includes whether this is GNSS or whether it's using pressure gauges to look at depth changes, as was done to monitor slope events in New Zealand, just sort of on the left here. The Hobbits experiments, that's from Laura Wallace's work. And on the right is an example from David Chadwell's work off Cascadia, I believe. And that's now been implemented in a few other places, is using these offshore techniques to go to see, the biggest part of the seismogenic part of the subduction zone, where we know the least, is offshore. And so monitoring the strain accumulation and release there was a big advance. And not just monitoring it, but also understanding the relationship between where strain is accumulating, whether it's accumulating, how it's released, when it's released, and how that's related to other kinds of activity like tremor, low frequency earthquakes, locking behavior, and potentially even large earthquakes. What's not on the slide here is there's also a realization that it may be related to other factors like the topography of basement that's being checked out, right? So there's the sort of tectonic and geological control as well. And that, while there hasn't been quite as much activity on the same problem in rift systems, a lot of the same questions are there and a lot of the same kinds of observations are there. So for example, in rift systems, this is a work from Becky Bendick on East African rift system. And new continuous geodetic campaigns have also shed light on the question of the relationship, and this is what Sarah, you were talking about a little bit, I think, it's the relationship between what's moving and what the fault, which faults are active, what's the pattern of faulting, and how's that related to the crustal deformation at larger scale. So digging in a little deeper, some of the other things that have come out sort of in probing these questions about why the faults behave the way they do, I would be remiss if I didn't mention some of the lab side of it, which has been a big thrust for at least one part of GeoPRISMS efforts aimed at understanding rheology. And so this is whether it's in the brittle frictional regime or deeper, it's the question of how do faults behave? Why might they lock? Why might they creep? How strong are they? Those kinds of questions. And so I thought long and hard about whether to include this slide because I don't want to throw shade here, but I think it's just useful to think about what amounted to a paradigm that lasted for about 2 decades. This idea that there's a transition and you have creeping in the shallow part of faults. They become seismogenic at a switch flips at 150 degrees. And then at 350 degrees, the earthquakes turn off and it goes back to being aseismic. And you can trace that paradigm back to 11 data points on a paper on westerly granite from 1995. So how many people here think that plate boundary faults are in granite? There are parts of Southern California, I know, that where you can make that argument, right? At least the experiments are done on hydrothermal conditions, so that's good. But the point is not like that this is wrong or anything. It's just it seems really simple in hindsight. But the GeoPRISMS program was one of the first places where it brought people together who were doing these kinds of experiments on things like glass beads and quartz powder and westerly granite with a community that was looking at real rocks or looking at geodetic deformation patterns, or going out and drilling into fault zones and saying, hey, you know what, these faults have clay in them, or these faults have a mix of serpentinite and clay in them, or whatever, whatever might be the case. And it turns out that the behavior is a little different than in granite. And so it may be a way to think about, right? It sort of sets the stage, even if we haven't answered those questions, to to me, there's a huge advance there in just bringing those communities together to think about the problem in a more educated way to address these questions of the complexity of the slip behavior. So people like Sabina Den Hartog, who was a GeoPRISMS postdoc actually, has worked on more realistic mixtures and shows some complicated behaviors. What's shown here is the A minus B, which is the whether something is capable of having stick slip behavior, in which case that's described by a negative value of A minus B. In other words, it gets weaker the faster it tries to slide. And so that's shown here as a set of laboratory measurements of that parameter as a function of temperature. So in her case, she sees this window where things could be could host unstable slip in a pretty broad temperature range, but it sort of kicks on depending on which curve you follow here for different materials and conditions, 200-ish degrees Celsius, right? And so again, the idea is not the details of the data set, but just the idea that it's using more realistic and appropriate materials and conditions. The same can be said sort of for the deeper part of the system. So it's not just about subduction zones, and it's not just about shallow faults, but again, this idea of probing the right materials under the right conditions to understand their rheology. And again, this is a case where a lot of the work wasn't necessarily funded solely by the GeoPRISMS program, but it was sort of the incubator for a lot of these ideas. In terms of exhumed faults and geological investigation, there's been some work, but it arguably hasn't been the biggest part of what was done in GeoPRISMS. So there's maybe a lot more room to do more here. But a lot of really fundamental insights about what do faults look like at depths that are equivalent to, or under conditions that are equivalent to, say, the in situ mid-crustal or seismogenic zone fault, whether that's in a rift system or in a subduction system. So this is work from Casey Moore that was published in 2007. It just shows some examples from Alaska, the Kodiak Island exposures that are thought to represent the modern plate boundary at depth of about 12 kilometers. Again, observations like structure, composition, vein architecture, all tell us something about the rheology at the time that this was. There have also been advances in linking some of these slip behaviors like tremor, slow slip, and observations of what it looks like, the seismic signatures or the resistivity signature. So here are a couple of examples of that. One, this is from Pascal Audet and others, Cascadia, showing the idea that there are these zones of low P and S wave velocity from receiver functions at depth that may be related to, they're spatially related to where slow slip occurs, and they are interpreted to represent something about fluids and low stress. Similarly, work that Hiroko has done at shallow depths where there are shallow slow slip events offshore Japan tells a similar story, but with a different kind of data set. So these are just two examples of that. There are more, right? So there's also the work that Jia Li did with Donna and Ann and others, Donna Schilling and Bissell and others on the right here, part of the elution imaging experiment, again, showing systematic variations in the reflection character. So what we see in imaging of the fault zone that may tell us something about how localized the deformation is. And they seem to correlate these patterns of what we see in images seem to correlate with slip behavior of the faults. So there are clues here. I don't think we've answered these questions, but again, significant advances in just making these connections. And then on the left is work from Christine Chesley, and I think she's going to be talking later today or maybe tomorrow about some of this work. This is controlled source electromagnetic. So again, it's sort of more of an image that's more directly sensing fluid content and connection of pores that allow electrical current. So this is work done with Sammer and Kerry Key and others. This is the Hikurangi Marge in New Zealand. You can see this sort of beautiful but very complicated structure of where the fluids are sitting at that margin. Another part of this, so this is again sort of thinking not just about subduction zones, but the same kinds of observations have been made in this system. So making these links between seismicity, structure, and fault evolution and localization. So in the same way that we have images of subduction zones and we can correlate what we see with the kinds of behaviors that the faults exhibit, there are similar, although sparser, observations from the rift systems that were the focus of GeoPRISMS. But for example, this role of fluids, there are some clear observations, again, work that James Muirhead did, and sort of this panel B and C down here for the East African Rift system, showing that there are places where it's very clear that the faults are connected and are venting CO2. And so, there's something there. And whether that's because, CO2 doing something mechanically to the faults, or is it simply a one-way thing where the faults form and they provide pathways? Maybe that's not answered, but there's an intriguing connection there. And likewise, just the broader question, this is on the left, this is Jim Gary's work, sort of the relationship between seismicity and fault structure, right? So it's a similar set of questions as addressed here, subduction zones at risk. So I'll leave it there. Again, I could go on and on and on with all the work that's been done in GeoPRISMS, but I think that kind of provides a little bit of a set of snapshots of the kinds of things where they're, where we sit in terms of the state of the science and what we've discovered through GeoPRISMS. I actually had a last slide that I started to make, which was, well, what don't we know? And I realized, well, that's not for me to do, because that's why we're here. So I started making that slide and I was like, what do you do, Demian? And I threw that one away. So this is the last slide. This just repeats what we talked about earlier. There.
Great, thank you so much. Are there any quick questions? We'll again have time for some longer discussion at the end of things. It's not right now. Is there anything to do?
No.
Okay. So let's move on to Harold. Oh, sorry. I'm trying to get rid of. Yeah. Is there?